Hello all. I hope you're all doing well. Yeah, my name is Amog, and I'm going to talk about equalization. I'm sure there's like a lot of content about equalization and the tap delay line and why we use it. But I wanted to get to the essence of it. Like, why exactly do we use it, and why do we have the system that has already been implemented? Like, why do we do that exactly? Let me get into it. Before I talk about the communication part about it, I just wanted to get into a bit of math before it. So this is called as the calculus of variation. So let's assume that we have a trajectory which goes from t1 to t2, and you have this function f. So f of t, y, and y dot, where y is also a function of time, and we want to sort of minimize the line integral of this function basically. So what we do is that it's not quite easy to do it directly. So we sort of use a trick called as variation. So what you do is, instead of finding the minima for this, what you do is you find the minima of y plus eta of t. Eta of t is like another function times epsilon, and this epsilon is going to be really small. When epsilon tends to 0, it maps to this function basically. Now, a choice of eta of t is such that it's differentiable. That's really important from calculus when they talk about Rolle's mean value theorem or Lagrange mean value theorem. It comes from this. So it's really important that this is the boundary conditions are 0 and it's differentiable. Um, Now, you have this y. Instead of y, we write it as y of t plus eta of t times epsilon, and we find the minimum of that. So to find the minimum, what do? We just take the derivative and equate it to 0. But in our case, we want to say that when lim of this function that we get, when epsilon tends to 0, then then we get back to this function. So which is why we find the derivative equal to 0, as well as substitute epsilon is equal to 0. I hope that makes sense. And the high level idea is that when you use this variation, you sort of make these different realizations to this function, and you try to, when you make these realizations, you kind of see where exactly the derivative is 0, because you have an extra function to sort of approximate it. And one thing to note is that you have this extra function. So when you try to optimize it, we just keep our fingers crossed and hope that this eta of t doesn't stay till the end, and our y of t to be a function of eta of t, because that would be nasty. So let's just hope that this eta of t somehow vanishes by itself. Spoiler alert, it is going to vanish, which is why that's the reason that I'm going to talk about it. Okay. Yeah, and one more concept before I get into the solving the optimization problem is that uh, I want to talk about intersymbol interference. So let's say in communication you send pulses, let's say this, but after it passes through these multiple filters, you're gonna get this sort of wavy sort of structure with like a taper at the end. Uh, you see that this taper is going to be an issue, because when you have multiple symbols that you're going to transmit with symbol duration t, let's say you send this and then you send this, over here it's going to look like this plus um, this. So it kind of degrades the effect of this positive pulse, and even let's say even a pulse after that, let's say it's positive, so it kind of degrades it. Sometimes it might enhance it, sometimes it might degrade it. In our problem, what we do is that we assume that we have a in this symbol interference of 2k plus 1 symbols, so that's k in the future and then k from the past, which which uh, sort of determine the decision that we're going to make for this pulse. So what we do is that we assume that the worst case. So in the sense that this is plus, let's say this is +1, we're going to assume that the rest of the k pulses are going to be -1 and then -1 on this side too. So that's like the worst case, and of course that never happens, but we are designing a system where we want to make sure that like we're able to decode for all possible cases. So before I get into this optimization problem, I just want to say that this is really important to take into consideration. So once you assume that we can still decode even though we have k symbols in the worst case, then we just need to think about the noise as the consideration and try to improve the SNR. So our goal, when let's try to construct the problem, our goal is to minimize the noise received by the received filter. So this sigma square is equal to 1 over 2 pi times SNN, that's the power spectral density of an AWGN noise. In our case, so SNN of omega times GR of omega square. Yeah, this is the how we find the standard deviation. This is eta naught over 2, and we want to just we have this filter from plus pi by t to minus pi by t. So we would have 1 over 2 pi times, this is eta naught over 2, so we just write we put it outside, eta over 4 pi times gr of omega square. Yeah, d omega. Am I missing something? Yeah, of course I am missing something. We haven't taken the multipath into effect. So we just assume that none of the symbols behind and or in the future determine our receiver, but they do. So what we're gonna do is we're gonna have this. I don't know if you've. I mean, from signal processing, there's a concept called as folding, where let's say we have this GR. We sort of divide it into slices of length 2 pi over t. So we sum them up. So this plus this plus this. So that's what exactly we do over here, because we have k symbols in the future and k symbols in the past. So over here we're going to tweak it. We're going to call it gr of k, where gr of k is gr of omega plus 2 pi k over ts, where ts is the symbol duration, or also the sampling rate, but we're assuming one sample per symbol. So k, this k goes from minus k to plus k, so we have 2k plus 1. So we're trying to minimize this. And let's say that we're given the x for each and every symbol. So we're given xn. So xn is equal to the same idea as above, the folding. We're going to get this xn is equal to x of n capital T. So we just took the inverse Fourier transform of this. Okay, now we assume that we have 2k plus 1 equations, like in the sense x constraints, we could call it, that this is one constraint, but we're going to have k of them, 2k plus 1 of them, and we want to minimize this. So we want to minimize it with these 2k plus 1 constraints. So what does that remind you of? Yes, that's correct. Lagrange. So Lagrange has the same idea. So every time you want to minimize a function with some constraints, you just do, let's say we want to minimize g with, let's say, one constraint k. So you want to minimize g plus lambda k. So that's what exactly we're going to do. And this I is going to be uh, g plus lambda k in our case. So let me write the whole equation down completely. Yeah, I'm going to take eta over 4 pi outside and also the summation k outside. So now we're going to get first the noise power. Plus lambda k by eta 2 eta times x of k of omega. So this is what we're minimizing, and these are the constraints, and this is lambda k. So we have k of these. Now let's apply the variation. So we're trying to find the best receiver. So we perturb gr of omega by eta of t times epsilon. And this xk of omega, we can write it as a product of gt of omega times h of omega times gr of omega. So let's plug that in. So let me just write these terms later on. Eta of omega, by the way, because we don't deal with t, we're dealing with omega in our case. We just perturb this again. And I'm just going to call the gt times h of omega as, let's say, q of qk of omega, just for simplicity. So let me write it here. So qk of omega is just the product, g, capital G, because gt of omega k times h of omega. The hk of omega is the same as h of omega. Yeah, it's just, okay. Now when we differentiate it, we get 2 times this, and then epsilon is equal to 0. So let me just directly write it as 2 times gr. And of course, you have all this summation integral and this coefficient, but I'm just getting directly to the point. So what I did was I differentiated this, so it's 2 times this term plus the eta of omega, because you differentiate this inner term, chain rule. And then for the first term, we substitute epsilon is equal to 0, so we just get this. And for the next term, lambda k